Welcome back. So we've talked about kinetics, we've talked about rate laws, what they are. What we have to figure out now is how do we use experiments in order to determine our rate laws? We said that's the only way to do it, is to take an overall reaction and use experiments to determine the rate law. So what we're going to look at is two different ways that are the primary ways that people who are trying to figure out rate laws do it. The first one is called the integrated rate law method, and the next one is called the initial rate method. So we're actually going to do those in the reverse order of what I just said. We're going to do the initial rate method first and the integrated rate method second. So how do we figure it out? Well, the easiest thing might be like, well, we know that for a zero order reaction, something where it doesn't depend on it, the rate's going to be constant over time. So if we look at a chart of concentration versus time, we might expect that that's going to be a line, because that's what we had for our initial chocolate one. We said, hey, we're just producing a pound or 100 pounds of chocolate per hour. We're using it up 100 pounds per hour. We had this nice, perfectly straight line. And boy, is that easily distinguishable from one where we're pouring chocolate. And we find that over time, the rate changes. Over time, this slope comes in and we got slower and slower and slower and slower. We're using less and less chocolate over time. So you're like, okay, well, I can just do that. I can just plot it. But then what if you wanted to distinguish between first order and second order? So n equals 2 and n equals 1. Well, both of those are curves. And you're like, well, the n equals 2 curve is curvier. And that's nice when you have an n equals 1 and an n equals 2. And by the way, n is the order. Right? When you have an n equals 1 and n equals 2 curve, then yeah, you can compare them. You're like, hey, look, this one's curvier. But if you have no idea and you only have one set of data, how are you going to do that? How are you going to know if you just have this red line or the orange line in the middle there? How are you going to know that that's a first order curve versus a second order curve? So we've got to figure out a different way of doing it. And like I said, one of the ways is called the initial rate method. We're still going to monitor concentrations versus time. We're still going to get that data, but then we're going to do something special with it. So how does the initial rate method work? Well, there's essentially 4 steps that you do. The first step is you're going to run an experiment and record initial rate. Now remember, initial rate, there's a little bit of judgment there. What does initial mean? And we just mean kind of that first little bit of data that you get. If you're recording 1,000 points per second and you're doing this for 15 days, it might be the first hour of data. If you're recording 1,000 points per second and the thing is done in half a second, it might only be the first 50 microseconds of data. So it just depends. But you're talking about that very starting area in your curve. You're recording that initial rate. Okay. Then you're going to change the concentration. Use brackets for shorthand there of concentration of one or more reactant. And then you're just going to run that darn thing again. And measure initial rate. Now, why would you do that again? Why would you change something? Well, if we're trying to figure out how does the rate law, right, which just calculates rate equals k times all these things, how does that rate law depend on concentration? Well, change in concentration is one way to figure that out. If I change the concentration, see how the rate's affected, then I can see, oh, what's the relationship between the rate and the concentration? And then the 4th step is what we're going to talk mostly about, is the comparing step. How do we actually take that data and compare one run to a different run? So I've got a very, very simple example down here. I've got 2 N2O5 plus 4 NO2s, goes to make 4 NO2s and an O2. So dinitrogen pentoxide makes 4 nitrogen dioxides and 1 oxygen. And we ran 2 experiments on that. One where we had an initial concentration of N2O5 of 0.01 molar, and then we calculated the initial rate. Now remember, when we're talking about these rate laws, for now we're only talking about reactants. We're not talking about products. There are reactions where the more products you have, the slower your reaction goes, but we're not going to talk about those. We're just saying, hey, our rate is only dependent on our reactants. Remember, we defined that rate is k times each one of our reactants to some power. We don't know what that power is. That's what we're trying to figure out. That's the goal of the initial rate method, is to find that value of m. Okay, so how are we going to do that? Well, we run the experiment. We run it again, and we compare. What did we do between experiment number 1 and experiment number 2? We doubled our concentration of N2O5, right? Going from 0.01 molar to 0.02 molar, we doubled it. So let's consider a few scenarios. So we've got rate equals K times N2O5 to the 0. Well, N2O5 to the 0, that crosses off because it's just 1, and rate is equal to a constant. Was our rate equal to a constant? No, it changed, right? Our rate also changed during this experiment, so we know that it's not 0 order. Let's consider another scenario. Rate equals K times the concentration of N2O5 to the first. Well, what would happen in that case? Well, if we just think about K as a constant, we don't know what the value of the constant is. I'm just going to make up a number 1 just for my brain, just as something to think of, which means that I can kind of take that out of there. So rate is just equal to the concentration of N2O5. So if we have 0.01 molar, then our rate would be 0.01. I'm leaving off units. This is just thinking. We're just thinking, but I'm thinking on paper right now. Okay, so that would be 0.01. But if I change the concentration to, silly computer, if I change the concentration to 0.02, and rate was equal to concentration to the first, I'd get 0.02. So when I doubled my concentration on this side, what happened to my rate? It doubled. And I could do the same thing. What if I changed it to 0.03? So comparing this one and this one, I tripled it. What happens to my rate? It goes 0.03, and it triples comparing those two. That's what first order looks like. When a reaction has a rate law that's first order in something, if you double the concentration, the rate should double. If you triple the concentration, the rate should triple. If you quadruple the concentration, the rate should quadruple. If you take the concentration down by half, the rate should go down by half. The same thing happens to rate as happens to concentration. That is what first order looks like. Okay, so is that what we had happen here? Well, we doubled our concentration. What happened to our rate? 4.6 times 10 to the minus 6 up to 9.6 times 10 to the minus 6. And you're like, I don't know if that's double. Is that double? Well, you know, if you divide those two out, your 10 to the minus 6s are going to cancel. And you get 96, or 9.6 divided by 4.6. 9.6 is pretty close to 10. 4.6 is pretty close to 5. 10 and 5 are halves of each other. If you're like, I really need to know whether those are exactly half from one another, then you just grab out a calculator and you divide the two. I am looking for my calculator, but I think my children were here earlier. All right, so what would you do? You just take 9.6 and you divide by 4.6 and you get, hey, look, 2.087. You're like, well, that's not 2. It's pretty close to 2, especially since we only have 2 sig figs. 2.1 is awfully darn close to 2. And so we're going to say this is approximately equal to 2. And so when we doubled our concentration, we doubled our rate. And that says we're probably first order. But let's go on. Let's say, what if we knew that rate was second order in N2O5? Let's again assume, just for thought processes, that K is equal to 1. Then we get that rate is equal to N2O5 squared. If it was 0.01, we get 0.01 squared. I don't know why my computer is doing this today. 0.01 squared, which is, that's 1 times 10 to the minus 9, this is 1 times 10 to the minus 4th. If it was 0.02, we'd square that, and you'd get 4 times 10 to the minus 4th. So when we doubled our concentration, going from 0.01 to 0.02, we didn't just double our rate, we quadrupled it. It was 4 times. What if I did 0.03 squared? I'd get 9 times 10 to the minus 4th. And so when I triple my concentration, I get 9 times my rate. 3 squared is equal to 9 if we just look at the numbers. Right? And that squared, that m there that we were looking at, that's our order. Right? And we said we knew it here, so that's why we're able to calculate this stuff. But that's what we're doing in the initial rate method. We're actually comparing these two experiments, and we're saying, in this case, since when we doubled concentration, going from experiment 1 to experiment 2, our rate also doubled, that tells us that we are first order in N2O5. All right? So let's check in. Let's give you a chance. We've run this reaction. A plus B is run in order to determine a reaction rate. A second trial is run where the concentration of B is doubled. The rate went up by a factor of 4. What is the order of reaction in B? Is it 0 order, first order, second order, or third order in B? Okay, so what did you find out? Well, hopefully you said, well, look, I went my concentration up by a factor of 2. And I'm trying to figure out my rate went up by 4. So what 2 to what power gives me 4? And you came up with, hey, it's got to be 2 squared. And that is true. And that tells us it's second order in B. And it really is this easy from a mathematical perspective. You really just can say, oh, I took and I doubled the rate, so let me just put that in parentheses and figure out what power I need to get the other one. Now, when we get to multiple things, when we're trying to find both A and B, it gets a little more difficult, but we can totally do it. And we're going to see some examples moving forward. But that's how we do it. Right? When we doubled our concentration, rate went up by a factor of 4, 2 squared. That concentration of 2 times 2 gives me 4 times the rate. All right, so that's second order in B. So here's a little more data. Looks a little more complicated. We've got hydrogen peroxide, iodide ion, and hydrogen ion is reacting in order to form the triiodide ion and water. And you just look at this balanced reaction, and you're like, wow, there's tons of stuff going on in here. And in some of the other ones, you're like, A plus B, let me just guess that that's first order in A and first order in B, and I'm probably going to be right. And you probably are, but not guaranteed. But this one's hard. You think we're really going to say, oh, it's first order in hydrogen peroxide, third order in iodide, and second order in H+? Probably not, because that would mean, and we'll see this later on in this chapter, that on a mechanistic scale somewhere, 6 things had to come together simultaneously, and that pretty much never, ever happens in the real world. So how are we going to do it? Well, we're going to do it by using the initial rate method. So we're going to look at sets of experiments, and we're going to compare them in order to figure out what the order of each of our reactants is. Now, we need to be able to monitor each of these reactants in order to do this, or at least know their initial concentrations. That's a nice thing, because we actually don't have to monitor them all as a function of time. We don't need to be able to monitor H2O2, I minus, and H plus as a function of time. We just need to be able to monitor one of them, and that gets us the rate. Because if you remember, the definition of rate is the change concentration of this over time, or the change concentration of this over time, taking into account stoichiometry. So it's really cool. I have lots of ways of getting the rate. I just need to know these initial concentrations, which is very easy to do for experimentally, because you just pour in whatever you pour in, and you know those initial concentrations. But I digress. So what do? We run the experiment. We change something, we run it again. But we ran 4 experiments this time, so what are we going to compare when there's 4 things? You're always comparing pairs of experiments. And the goal is to find a pair of experiments where only one thing changed. There always will be one, where only one thing changed. So let's just look at experiment 1 and experiment 2 to begin with. We're going to blow those up here. And experiment 1 to experiment 2, our H2O2 changed. Our I minus didn't change, and our H plus didn't change. So right, since they didn't change, whatever contribution they make to the rate is going to be the same in both experiments. So the only thing that changed is H2O2. So the hydrogen peroxide concentration changing is the thing that's going to cause the rate to change. So what do? We look from experiment 1 to 2. We took the concentration of H2O2, and we went 2x, and the rate also went, what did it do? 2x, right? 2.3 times 10 to the minus 6 divided by 1.15 times 10 to the minus 6 is 2, if you type that in your calculator. Remember, you can kind of leave off the 10 to the minus 6's since they cancel, and you get 2.3 divided by 1.15, and okay, that's 2. So when the same thing happens to the rate as to the concentration, what does that tell us? Hopefully you came up with first order. So we can say that the reaction is first order in H2O2. Silly computer today. Since rate doubled when concentration of H2O2 doubled. And on tests and quizzes and things like that, I want to see something like this. I want to see a justification, not just, oh, here's a table and it's first order H2O2. Right? Tell me why. Well, because when I did this, this happened. So you can see your handwriting doesn't have to be the best, but you do have to justify it. It's first order in H2 since the rate doubled when the concentration doubled. All right, so we now know that our rate law, I should have written this to begin with, is H2O2 to the m, but in this case we actually have already figured that out, to the first. We know it's going to be I minus to some other thing, and we know it's going to be H plus, and right, mn, you'd like to think it was O, but if you write O, it kind of looks like 0, so people usually use P next. Okay, so if I wrote that earlier, it would have been mnp, but we determined that m is equal to 1. So now we got to figure out n and p. So what we're going to do is we're going to look back up at that table up there. Let's blow this guy back up again. We've already done experiment 1 and experiment 2, so we can't use those again. We want to find another set of experiments where only one thing changed. Well, you're like, let me just go down the table. Let me look at 2 and 3. When 2 and 3, H2O2 changed and I minus changed. That's not the best one. We might have to use that, and sometimes in the more complicated cases we do. But let's see if we can find a way of not using it. So we do 3 and 4. 3 and 4, H2O2 stays the same. I minus changes and H plus changes. Okay, well, that's not good. So you're like, oh, well, maybe that's it. Maybe I'm just done and I've got to do some more complicated stuff. But no, this is our first example. There's got to be something a little bit easier. So sometimes, even though we've already used experiment 1, we only compared it to experiment 2. We can also use experiment 1 and compare it to experiment 3. So let's do that. Experiment 1 and experiment 3. H2O2 stays the same. I minus doubles. H plus stays the same. Yay! We found it where only one thing changed. And so what did we do? We took the concentration of I minus and we doubled it. And what did we do to our rate? It also doubled, because you remember from our last one that 2.3 divided by 1.15 is 2. And so we can also say that, when we took the concentration of I minus 2 times, we got a rate of 2 times. And so we can say it is first order in I minus, since rate doubled when the concentration doubled. And again, this only works in the case where I minus is the only thing changing. If I picked one of those sets of experiments where 2 things are changing, I'd have to take into account 2 things at the same time. Totally doable, but a little harder. All right, so we now know that our rate is K H2O2 to the first, I minus to the first, and H plus to the P. We just got to figure out P. So we have to find an experiment where just H plus is changing. You see one where just H plus is changing. Well, experiment 1 to 4. H2O2 stays at 0.01, I minus stays at 0.01, H plus doubles from 0.0005 to 0.001. And what happens to our rate? When we doubled our concentration of H plus, absolutely nothing happened to the rate. And if we change a concentration and nothing happens to the rate, we call that 0 order. And so we can say, when we did H plus 2x, rate was 1x, right? It stayed the same. So this is 0 order in H plus, since the rate didn't change when concentration of H plus doubled. So there we go. Not the best handwriting, but you get what I mean. We doubled the rate, or doubled the concentration, nothing happened to the rate, so it's 0 order. So we now know that rate is equal to K times H2O2 to the first. We don't have to put a 1 there, because right to the first is just basic like that. I minus and H plus to the 0. Now, a lot of people, right, since h plus is 0, a lot of people will just leave that off, and they will just write that. Either way is fine by me. When you write h plus to the 0, it really tells me that you didn't leave that one out. But this is also correct, and most people will write it this way. They'll just leave out the h plus since it's 0. Now, how are we going to figure this out? Well, we're going to figure it out by, we figured that out. The next thing we might need to figure out is what is the value of that rate constant? Turns out rate constants are really, really useful to have, because if you know them, for the future, you just tell me some concentrations, and I can tell you exactly how fast that reaction is going to go. You want to figure out how to triple it? If I know K, I can tell you here's how you triple your reaction rate. Very, very nice to know K. How do we figure out K? We figure out K from our experiments. Now, we've got 4 different experiments. Whoa, way up here. 4 different experiments to choose from. How do we pick K? Well, on a test, I only need you to pick one of them, because you have a limited amount of time on a test. In real life, right, when you have 4 pieces of data, what do you use? You use all 4 pieces of data. So you'd actually calculate K for each one of those experiments. You do some statistics, and you're going to do that in lab. But we're not going to do that here. We're going to just pick experiment 1. Our concentrations were 0.01 and 0.01 for both H2O2 and I minus, and our initial rate was 1.15 times 10 to the minus 6. So we get that 1.15 times 10 to the minus 6 molar per second, remember that's the most common unit for rate, and we saw that above, is equal to K times my H2O concentration. H2O2 was 0.010 molar. Notice how I'm putting molar units in there now, because I actually have numbers. 0.010 molar. You have to have those units in there. It's not right to just put 0.01. All right, what do? You multiply that out. You get K times 1 times 10 to the minus 4th molar squared is equal to 1.15 times 10 to the minus 6 molar per second. You divide both sides by 1 times 10 to the minus 4th molar squared. And you type that into a calculator. And if you type that into a calculator, you're going to get, you're going to get 1.15 times 10 to the minus 2 is equal to K. Is that great? No, we got to figure out the units. And what do we have? We had molar per second. It's the ugliest M I've ever seen, so let's do that one. Molar per second divided by molar squared. And so our units actually end up being per molar second. And if you remember, the units of K are the units of K. You don't really have to worry about them too much. All right? So that's how we would do it. We'd do all that math out, and we figure it out that way. All right. Let's do another one. Here, initial rate method number 3. I encourage you to pause and try to figure this out. What is the order of reaction with respect to H+? So look at that data. I encourage you to pause. I'm not going to make you do it right now. See if you can figure it out. Did you really pause? Come on, just pause. Try it. You can do it. I know you can. Okay, so we have to find an experiment where only H+ changed and nothing else changed. So if we look at 1 and 2, bromate changed. So nope, not the one. How about 1 and 3? Nope, bromate and bromide changed. Nope. How about 1 and 4? Yay! Look, if we look at 1 and 4, bromate, bromide stayed at 0.1, and H+ doubled from 0.1 to 0.2. So experiment 1 to 4, we've got H+ doubled. And what happened to our rate? It went from 8 down to 3. What? How can it go from 8 down to 3? I doubled my concentration. Why did my rate go down? Here's where you do have to pay attention to your orders of magnitude. And some people have trouble dividing scientific notation in their head. Totally understandable. Type it in your calculator. It's okay. So if I type in 3.2 times 10 to the minus 3 and I divide by 8 times 10 to the minus 4th, I should get 4. 4 times 8 is 32. So 4x rate. So I doubled my concentration. My rate went up by 4x. You can think about it like this. 2 to what power gives me 4? Well, 2 to the second. So m equals 2. And we have that this is second order with respect to H+. we're not going to find k for now. All right, last one, and this one is for you to do. What's the order of this reaction with respect to Br minus? Same reaction, same data as the last slide. We're trying to find Br minus. Go! Don't you just love those faces? All right, got to find an experiment where only Br minus changed. Well, the only experiment where Br minus changed was that one, so it's certainly going to be experiment number 1. What else is it going to be? Probably experiment number 2, because you see BrO3 didn't change, H plus didn't change. So what did I do? I doubled my concentration of Br minus, and what happened to my rate? 1.6 times 10 to the minus third, 3.2 times 10 to the minus third. If you type that in your calculator, the rate went up by 2x. And so we can say when the same thing happens to our rate as happens to our concentration, we always say that is first order. And you know, on a test, you justify that. You say it is first order in H plus, oops, oh yeah, Br minus. I was writing it right, Br minus, because when Br minus doubled, rate also doubled. Pretty simple, one sentence justification. All right, hope that was helpful. We'll see you again next time. Bye.